This one, I've heard about GrAiNZ a few years ago and always wanted to come, and so it's such a privilege not only to come but to be asked to speak, which is a little bit of a shock. And they've asked me to speak about soil, and I guess because that's what I'm interested in, and it maybe relates to what you're interested in. Well, hopefully it does, and if it doesn't now, hopefully it will by the end. Some of the stuff I'm going to cover a lot of ground in a relatively short period of time. If you want to know more, come and grab me during the day. About any particular topic. If you know, a lot of you may have covered a fair bit of this, but hopefully even if you've already heard it before, it might galvanise you a little bit more, ready for the next couple of days of demonstrations and talks. So I live on a little farm in southern Tasmania, Fat Pig Farm. It's 70 acres. We call it our big farm. I just met a woman whose husband built the house on our first farm. That was our small farm, 22 acres. We sold it a few years ago. So we call this our big farm, 70 acres. So in Tasmania, where I live, that's big. It's a long rectangle. There's an entry road here. The only road originally was to this big shed. There was only one shed on the farm of any substance. It's actually 39% is for wildlife, so through the middle and the top bits of bush. We've got a market garden down here where we did grow wheat once upon a time. 4 15-metre long garden beds, 80 centimetre wide garden beds, and I think I made 4 loaves of bread. This is our house. It's about halfway up. So we have a market garden, we have pigs, we have a little bit of heritage orchard. We grow about 50 varieties of apple. It all used to be apple growing country in that little part of Tasmania. We have we have a little restaurant on the farm. This is our restaurant, and so for those in the room who are bakers, we have an Allen Scott oven, a 22-loaf Allen Scott oven, built by Dennis. Oh, his brains, we call it the Dennis, after Dennis, the bricklayer who built it. I can't remember his last name at the moment, but someone will yell it out. So anyway, I won't talk much about us. I want to talk about other stuff. Soil. Soil only matters if you like to sleep indoors, eat and clothe yourself. Okay, so it's kind of important. This is soil, pretty boring to look at. I give talks on soil all the time, and a journalist I was chatting to one day said to me, "Matthew, you're trying to make soil sexy." And let me tell you, soil's as sexy as colon cancer. And I haven't had colon cancer yet, and I'm hoping not to. And I don't know, I doubt it's a great thing to have, but I also know that soil has things to recommend it, and I doubt colon cancer has much to recommend it. Anyway, this is a rainforest, so it's much easier to get people interested in rainforests because they're pretty, they're great to walk in. You get those beautiful smells when you walk through. It gives you visceral pleasure. This is the Great Barrier Reef. If you get a chance to dive over the Great Barrier Reef, what's left of it, okay, it'll give you visceral pleasure. You'll have a reason to want to protect it. But soil's not quite like that. The best we can do with soil is make a love heart out of it. Oh, I love soil. Right, it's pretty boring to look at. Doesn't give us great joy unless you're a soil nerd. There might be a few in the room, but most of us are a bit more normal than that. The reason I got interested in soil is because of this. I'm always hungry, okay? And so there's no food without soil. 98, 99% of the calories that humans eat come from the fact we've got topsoil and that it occasionally rains. That's the difference between humanity existing and not existing, is that little magic bit, the dark bit, when you cut into soil, when you cut into the ground, the topsoil's the dark bit. The fact that exists and it rains is the difference between humanity being here and not. All life on Earth, pretty much. When we grow food and we think of soil, we think of the Malakadi. The Malakadi have been feeding themselves on our patch of land for about 42,000 years, probably longer by current estimates, it's 42,000 years. So we tried to take a longer-term view of soil. I was working with a market gardener a couple of years ago, Nadia Dante, who was our market gardener for a few years, and she told me, growing food, mate, growing food's not rocket science. So 15 years ago, I'd never grown much more than a bunch of parsley and a couple of tomatoes, and then we decided to buy our little first farm in southern Tasmania. And she, this woman who came to do our market gardening, she said, growing food's not rocket science, Matthew, it really isn't. It's way more complex than that. It's really complex. Don't be an idiot. So that love heart of soil, so what did it contain? It contained some rock minerals, but then it contained all of this life. So when we talk about healthy soil, healthy by definition means alive. like super duper alive. So take a teaspoon of soil, like the amount that fits in the end of my thumb, there can be more living things than there are humans on the planet. 1 teaspoon of soil, 10 billion living things. And those things are important, and we'll get to why they're important a bit later. But these are the sort of things you can find in a couple of handfuls of soil. 5,000 insects, protozoa, nematodes. Nematodes, microscopic worm-like creatures. I had never heard of them 10 years ago, right? A nematode, didn't even know what it was. Nematodes are the most abundant multicellular organism on the planet. There are more nematodes on Earth than pretty much anything else, apart from bacteria, viruses, okay? Nematodes, if you link this, for each of us, there's 60 billion of them. If you made a conga line of nematodes, so if you link them all together, that line of nematodes, they would stretch out past the edge of the atmosphere, out past the edge of the solar system, out all the way to Alpha Centauri, 4 light years away, right? 4 light years away and back. That's how many nematodes there are on Earth. 90% of them live in soil, right? And they have a role. They have a role in soil. And we'll see a little bit in a moment one of those roles. So you've got the nematodes. Bacteria, they're pretty important. Single-celled organisms. There's lots and lots of them. But this one's pretty important. So in a couple of handfuls of soil, you can have 100 kilometres of fungal filaments, fungal hyphae. And they're really important. Fungal hyphae can do stuff that we're only just beginning to understand in terms of science. So there's a lot going on in soil. These are fungal hyphae. So when you think of a fungus, think of a mushroom, but actually most of the fungus 90% of the fungus on Earth live in soil, and they exist as fine threads. Now these threads, they're about 1/60th the width of a root hair, of a plant root hair. And these are all some different styles of fungal filaments. These are little sticky nodes. This is a little 3-cell loop. There's a join, there's a join, there's a join. This is like a lasso. And this is going to sound a bit crazy, but fungi can lasso nematodes. So the microscopic worms, nematodes that exist everywhere, they can move through soil, right? A plant's roots can only move through soil really slowly. Fungi can move through much faster. Nematodes and worms can move through soil really fast. And they're moving nutrients around. Now say you're a plant and you need nitrogen, right? And this is going to sound crazy, but you're welcome to look this up. Plants can talk to each other and they can talk to the underground ecosystem. So if you're a plant and you say, I want some nitrogen, say, nitrogen's a superfood for a plant. If you're a plant and you need some nitrogen, you can actually talk to the fungi that are around your roots and say, can you go and find me some nitrogen? And the fungi will say, maybe. How will I find nitrogen? This is, I've never used these much before. This is that 3-cell lasso on a fungi. This is the fungal hyphae. This is the fine thread of fungi. This is strangling a nematode. This is a fungi who's been asked to find some nitrogen, or maybe it needs nitrogen for its own purposes, but it's probably getting it for a plant. It's strangling a nematode, because a nematode like us has nitrogen in it, protein in it. It's going to strangle the nematode, it's going to suck the nitrogen out and pass it back along this hyphae to the plant roots, right? This is an electron microscope picture of that happening. So when we talk about life under soil, it's actually, it's not just some kind of fairy tale and, oh, it's really nice that it's there. It's actually got a purpose. These are all different sort of things that happen. There's the 3-cell bit. Here's nematodes being attacked. Here's a nematode. There's sticky ends to some of the fungi, and this is a nematode that's actually escaping. They've managed to get 3 photographs as the nematode manages to wriggle away from the fungi in those last 3. There's other things in soil, and some of them aren't microscopic. And I love these because hopefully we've got a guy coming to our farm later in the year who takes photos of this stuff. So an American guy worked out in a single footfall under one of his boots in an Oregon forest, there can be 16,000 critters that have jointed legs. And when we talk life in soil and bacteria, single-celled organisms, a bit boring, microscopic worms, and we can't see them, these are actually things on jointed legs. So insect-like creatures that look like that. That's a springtail on a snail egg. That's a snail egg. And there are these macro photographers who take photos of all this stuff. One of them's a guy named Andy Murray, and he's not a tennis player. And that's his source, that's his website. There are others, Frank Ashwood, who hopefully will come to our farm later in the year. So how do we connect non-growers to soil? It can be hard. I like to tell stories. And one of the things you can do is tell stories about food. So if you're a grower of grains or anything really, you can tell stories of your soil to get people interested. And if you're a producer, a baker, you can tell stories of the people who grow. But I'm going to tell you a couple of other little stories before we get into a little bit more nitty-gritty of why we should care about soil. One of the reasons people should care about soil is that over half the antibiotics used in human medicine were born in soil. Okay, that's where we found them. We actually know, I was giving a talk a couple of years ago online. Remember those days? Jesus, I'm glad you're all here. This is so nice. Do it in person. And at the end of this talk on soil, some Queenslanders came on and they said, "Oh, Matthew, can you tell me about anywhere in the world that you've heard of a certain population who are more resistant to certain diseases based on soil?" And I'm like, "What are you talking about?" Like, it's just like crazy left of field question. And I said, "Oh, no, but why?" And they said, "Well, because we are researching the next generation of antibiotics. We know they exist in soil. We just haven't found them yet. And you can actually mail your soil sample to these people in Queensland and they will analyse it to see if they could find the next generation of antibiotics. Because 98% of what lives in soil is unidentified by science. 98% is a mystery, a complete and utter mystery. Soil is an antidepressant. There's a bacterium in soil, when you inhale it, it actually has an antidepressant effect on your brain. It releases happy hormones in your brain. Like this is going to sound airy-fairy. I'm happy to go through any of this later and give you references for any of it, but that's one of the reasons why you never meet a grumpy gardener. There's this chemical in soil, it's so powerful, they're testing it as a treatment for PTSD, right? That's how powerful it is. Soil inoculates our immune system, so I was doing some work with a charity called Mother's Babies. Mother's Babies are trying to give newborn babies the best chance at a healthy life through immunity, right? And the three big ticket items are full-term natural birth, if possible. Not always possible. Breastfeeding for as long as possible, if possible. Not always possible. The third big ticket item is contact with soil in the first 3 months of life, right? It's almost like we've designed, like we evolved to be around healthy soil, right? You know, it's hard to believe, isn't it, that would actually inoculate our immune system. So there are things that live inside us, things like Bacillus subtilis, that exist in soil in almost the same level as they exist in our gut. There are things that were born in soil that actually help inoculate our gut and give us our microbiome, our immune system. Soil affects the climate. So we like to think of, you know, when you're flying somewhere and you tick a box that says, you know, offset my carbon emissions, someone's going to plant a tree, maybe. If you saw that map that came out last year, where they're planting all the trees tends to be where trees don't grow. But anyway, the theory is someone plants a tree for you to offset your carbon emissions. So how does soil affect the climate? Well, actually, trees, yeah, they're kind of important, but soil holds about 4.5 to 6 times more carbon than all the plants and all the animals on Earth put together, right? Forests matter because what trees are doing is taking carbon out of the atmosphere and putting some in their structure, but they're actually putting heaps and heaps into soil. It's actually soil that does the heavy lifting. So soil can affect climate. Soil also affects weather. And this one I love. So when I was getting interested in soil and I was, you know, I started researching, you know, trying to grow, how to grow food better on our farm. I discovered this guy in America, David Sands, and I love this kind of science. So David Sands, he was researching wheat. Some of you might have heard of that, right? It's a grain. They grow it in America, apparently. He was researching wheat blight in the 1980s, I think it was. So 1980s, wheat blight spreads through is caused by a bacterium that gets on the leaves of the wheat, and as the temperature drops, this bacterium could ice crystals, frost would form at a warmer temperature than normal. The ice crystals would form around this bacterium and weaken the plant's cell structure, and the bacterium could then invade the plant, right? So this guy wants to grow wheat without wheat blight. So what he does is he gets an entire paddock in Montana, and he tests the soil, can't find the bacterium there. Tests the wheat, it's free of the bacterium there. And then he also tests the water, and there's no bacterium there. Great. He's going to grow a paddock full of wheat, no bacterium, no wheat blight from that bacterium. Plants the wheat, no problem. Then all of a sudden, at a certain point, he discovers wheat blight. But it doesn't start on one end of the paddock and then gradually spread. It happens to the entire paddock all at once. And he's like, oh my God, like where could that come from? And he thinks, well, it has to come from above. Has it blown in, or what's happened? And he has this idea that maybe if ice crystals form at ground level at a warmer temperature around a bacterium, can that happen up in the atmosphere, higher atmosphere, where clouds form? And he's like, well, because at that stage, people didn't think that bacteria could fly into the atmosphere, and diatoms and all sorts of stuff, and viruses can fly from the atmosphere. At that point, they didn't know that could happen. Anyway, he goes, I love this kind of science because it's crazy. He's going, well, maybe it's, maybe this bacterium is the genesis of rain. Maybe, because to have rain, you need ice crystals to form in clouds for rain to form, right? So what he does, he goes up in an aeroplane, shoves his hand out the window, right? Gets frostbite, 3 kilometres up in the air, clutching an agar plate, scooping. I don't think he's flying the plane at the same time. He's not. It's like madness, right? Comes back down to earth, takes the agar plate, the petri dish, incubates it, and finds that bacterium, the bacterium actually has, he finds it in the clouds. This single bacterium that he was looking for. There it is in the clouds. And so he goes, well, probably there's this thing called bioprecipitation where we know that ice crystals can form in clouds around inorganic things, dust particles, but it happens at a lot warmer temperature around organic particles. So maybe things on Earth form the genesis of rain. And the entire world went, what? What? They did nothing. They didn't believe him for about 25 years, I think it was. It wasn't until Montana State University, same university where David Sands went, they had a massive hailstorm. The technology had moved on. They actually had this hailstorm. One of the other researchers took a whole bunch of hailstones that landed on the campus and then cut them in half and found in the centre of every single hailstone the same bacterium that David Sands had found. And it was suddenly like, oh my God, things, biologically active soil and biologically active plants, so forests, have a reason to affect rainfall. So soil affects climate. Affects weather. I already told you that one, 98% of all the calories we consume come from the fact we have topsoil, but we're losing topsoil pretty fast, 30 to 40 times faster than it's being made, okay? If you plough the land where you grow your grains, these are global averages. It varies a lot depending on where you are and who you are and how it's done, but if you plough the soil, you generally lose, on average, your topsoil 100 times faster than nature can make it. Nature's always making topsoil, weathering rock and organic matter, but plough the soil, on average, 100 times faster losing it than gaining it, right? I'm no maths genius. No, those numbers don't add up. If you do no plough, no till, you can still lose it, on average, about 15, 20 times faster than nature makes it. So it's still a losing game, generally, around the world. I want to play a little game. I was on Twitter. I'm so young and groovy. I'm on, with Elon. Twitter, I discovered it a few years ago, and when I discovered Twitter, I discovered that these people, was a big drought on the mainland, and a whole bunch of farmers were comparing their farms to some photographs that had just been released, the first high-res photographs of Mars. The Mars rover was taking really high-res photos. So I want to play a little game. Is it Menindee or is it Mars? Menindee or Mars? Mars. Menindee. What's that one? Yeah, that one is Mars. What about that one? Menindee? No, it's Mars. That's Menindee. Now, this one, see the grass? I know it's a bit hard to see from there. There's a little bit of grass there. They haven't quite got grass on Mars yet because even in Menindee, they've got soil. Mars does not have soil, Okay, no matter what you read, Mars, the moon, do not have soil, cannot have soil, because soil needs soil life. There is no life on Mars. There is no life, or certainly not the amount of life that we would find in what we would call soil. Rightio, this is also from that time. As the dust storm settles, grazers need to remember that the next drought is inevitable. New South Wales in that same year, 2020, might have been 1919, I can't remember when the drought was kicking, right? 8,000 hours of dust storms, 330 days equivalent of dust storms. It's inevitable, according to someone. 650 tonnes moved from these sheep yards. I always wonder what topsoil looks like. I found this photo, it looks pretty interesting. That's just soil being moved around. When soil moves, it's dead, okay? So as soon as you move it around, you blow it or wash it away, it's dead. Annually, Australia loses 2.9 billion tonnes of topsoil every year, right? Every year we lose that much. So you put that into railway carts. This is an iron ore cart or something. But imagine all the topsoil Australia loses every year. I've been trying to find the amount we lost through the floods last year, which would be big, way bigger than this. But anyway, if you put that into railway carts, that train full of Australia's topsoil would stretch around the world. This is just 1 year's worth of topsoil. It would stretch around the world 15 times. Right? How you grow food matters. This is the latest State of the Environment report, the assessment from 2021. So this is the one that the coalition government didn't want to release, and as soon as the Labor government got in, it got released, but it was about a year late, I think. This is the assessment for soil health in intensive land use zones. So this is cropping areas. This is where you grow your grains, where you grow your vegetables, arable land. We're not talking grazing land. This is your arable land where your grains come from. We're poor, and that arrow means getting worse. They don't have worse than very poor. So I don't know where we're going. Well, I do, because on average, around the world, we lose 9 kilograms of topsoil for every breakfast, for every lunch, for every dinner that every human on Earth eats. That's how much we lose, a bucket full of topsoil. Imagine that when you have your cornflakes tomorrow. In WA, salinity's ruined about 1 million hectares of growing land. There's about 10 million hectares of land that they reckon in Australia is going to lose its A horizon, essentially its fertility. It's going to cease to be fertile in the next 500 years. It's a lot of land. So the choice is ours, you know. So there's reasons to hope. I want to tell a bit of a personal journey. This is me, our old farm. So just to the right of that photo is a house that a bloke named Dominic built, beautiful little farmhouse that I lived in. I put my pigs down here. There's now a dam there, funnily enough. But it rained 80 millimetres overnight and my pigs destroyed that area. I'm not proud of it, but I'm showing you that photo because this is what humans have done forever. Use a piece of land, grow something on it, bugger it up. And you know what we did with that farm? Sold it and moved on. So the world has abandoned about 40% of the land they once farmed since agriculture began. Most of that in the last 200 years. What we've tried to do, and we're no experts, we're just having a crack. This is our farm, April 2016. So you can see it's a bit of bare earth in our pig paddocks. These are pig paddocks here. This is a garden. This is very patchy here. I took this shot in April 21. And you can see there's no bare earth in the pig paddocks, much longer grass. I don't know if you can see that, but it's much greener. And then I realised that was actually a wetter year. So I went back and took a photo in 22. That was the hottest, driest summer on record. And so we've actually changed that quite a lot. You can still see decent grass growth, not much change in here, a little bit of change in here. But yeah, quite decent sort of growth over the 6 years. So it's possible to heal soil because grass is green living plants are a representative of soil health. My job on our farm is to watch grass grow. That's actually what I do for a living. What our aim is on our farm is we don't use soil to grow plants and animals. We use plants and animals to grow soil. That is our intention with our farm, which is not possible for everybody, but it's what we do. This is our garden. Over 10 years, so it was just a paddock and now it's quite fertile. For those who are in the game, our organic matter went up from about 4% to about 13% was the latest measurements from the garden. So that's just a back shot of the garden. I just wanted to show you a picture of the fractals, just love that. This is pretty important. These are the bigger things we can see in soil. This is compost. And so it's you know, on small scale, in the garden, we can use things like compost. It's much bigger on broad areas. And you're going to hear from some people who know more about this stuff than me. These are our pig paddocks, 2012 to 2014. So you can see there's a bit of bare earth here. This is actually where our garden's going to be. And you can see I've put in a shed and there's some garden beds, but it's a bit hard to see. But there's these rows here that are starting to appear. And what we didn't know is where we put our pigs is actually an old orchard. So over time, by saying, oh, let's have no bare earth, let's move our pigs around, let's look after the soil, we've started to see big changes. So this is the same fence here as there. There's no bare earth, and see all these trees. So now for every kilogram of pork we produce, we sequester, we take out of the atmosphere 77 kilograms of carbon dioxide. Part of that's stored in the trees and part of that is stored in soil. So we're not saints, I wanted to show you that. So this is a very recent photo. This is just between two of our dams. This is erosion. So we're trying to look after topsoil. But, you know, I sometimes look at our farm and go, oh, we're not losing, you know, how many kilos are we losing for every breakfast, for every lunch, for every dinner? Well, we're still losing topsoil because, you know, this is the topsoil here and then we are now eroding down, and that's widening out. And I haven't managed to come up with a solution. It's quite a big drop between one dam and another, and we end up with this massive erosion. So we're no saints. On 70 acres, we grow enough food to feed for 10,000 meals a year. So when I say a meal, we're a mixed farm because we have the market garden. We do 30 to 50 species of annual vegetables. We do about 30 species of perennials. So it's quite a mixed diet. We milk cows, we have pigs, we have goats, and we have beef cattle. We're carbon negative, meaning we sequester over 100 tonnes of carbon dioxide a year, probably close, somewhere between 100 and 150 tonnes a year. And part of that's through soil, and part of it's not. This is our grazing land, so you can see this is an abandoned vineyard up here. But you can see the start of some other stuff. We've done some, we planted a cover crop through the middle of our pasture just to see what happened. And this is what it looked like when I grazed it. That's the first of 3 grazing. You can see the tick beans. There's also some mustard in there. It was a 9 species mix. Probably should have done a few more. Couldn't get any tillage radish, daikon at the time. That's the first of 3 grazings. This here, so you might have heard of plants that store nitrogen. This is a broad bean, tick bean. This is the roots. So wherever you've got lots of stuff clumped around the roots, that's a really good sign because the soil ecosystem will clump around the roots much more with healthy soil. These little baubles, when you hear of a legume, a pea or a bean storing nitrogen, they don't actually store the nitrogen. It's bacteria. It's the ecosystem around the roots of the plant that does the storing of the nitrogen. So these are full of rhizobium bacteria. Right? They are, and what they do is they use energy that the plant has got from the sun to take nitrogen out of the air, and that's essentially nitrogen superfood for plants. That's a beautiful form of it that will stay in the soil once the broad bean has been nibbled by my cows. They go pink. That's a form of, you know how our blood goes red with haemoglobin? This is a form, it's called leg haemoglobin. Okay, so it's a leguminous haemoglobin. So it goes pink because when there's stored enough nitrogen, there's also oxygen that's fixed in there. And leg haemoglobin is what they're using, I think, in the Impossible Burger to make it bleed. Right, I want to just really talk about briefly about photosynthesis. So, when I was at school, photosynthesis. So a plant, I was taught that what a plant does is it uses the sun's energy, takes in the sun's energy, and then it breathes in carbon dioxide and it breathes out oxygen. And that's really handy for us because we breathe in oxygen and we breathe out carbon dioxide. So plants help us to breathe, right? That was what I was taught. And that's kind of true, and it's kind of not, and it's kind of irrelevant because it's not actually the oxygen-carbon pathway in that sense that is important in terms of photosynthesis. So all green living plants, what they're doing, every green leaf, every time you see a green leaf on it can be grasses, it can be wheat, it can be a tree. A chloroplast is like the original solar panel. They take in the sun's energy, a photon of the sun's energy hits that chloroplast, and they use that energy, yes, to draw in carbon dioxide, and they take up water from their roots, and they do breathe out oxygen. But the important thing that happens is the plant takes in carbon dioxide, takes in water, uses the sun's energy, splits those apart and recombines them as carbohydrate. a plant makes sugar out of thin air, out of that. When you eat a carrot, 99 point something % of that carrot used to be fresh air and water, right? That's the miracle. Yes, there's some other things in there, some calcium, some magnesium, some nitrogen, whatever, but the vast majority is sugars that a plant makes out of thin air. Now, that's nothing else on Earth can do that apart from algae in the ocean, right? So you and I, there's a couple of very small caveats to that, but essentially that's where energy gets converted into digestible form. So you and I, well, take me as an example. I'm of Scottish and Welsh ancestry, right? I am a very pale person, right? If I go and lie out in the sun and I attract all the sun's photons, all I do is get sunburned and then get a melanoma, right? That's as good as it's going to get. A plant turns the sun's energy into sugar, energy in digestible form. It's utterly amazing. That's the start of energy on Earth in a digestible form for us. And remember, the oceans only produce about 1–2% of the world's calories. So they loom big in our imagination, but they're not producing much. And in fact, most of our oceans would become less fertile if we didn't have topsoil, because most of our fisheries rely on fertility and nutrients that are washed off land. Anyway, what this plant is doing, as all plants do, is it's turning carbon dioxide and water into carbohydrate. It's using, say, let's do some global averages, 70% of its energy it's using to build itself, to fight disease, to fight stress if there's wind or whatever. And it's building its structure. 30% of what the plant produces, of the sugars it produces, it is dribbling out through the ends of its roots. Because 10 billion living things in a teaspoon of healthy soil cannot make their own food. Just like us, they need energy in digestible form. So the plant is actually dribbling out mostly sugars, but sometimes amino acids and even fatty substances. The plant actually dribbles out things called exudates from its roots to feed the underground ecosystem. So that fungi I showed you before that was strangling a nematode and passing the nitrogen back to the plant, the fungi's not doing that because it's a nice guy. The fungi's doing that because the fungi can't produce sugar. The fungi needs sugar from somewhere. So the plant, the way it works is this underground economy. The plant says, I need nitrogen. Can you go get me some nitrogen? The fungi says, what's in it for me? And the plant says, well, guess what? You need sugar. I've got sugar. How much do you need? And that's the transfer. So it's a two-way street. The rhizosphere is the area around the plant roots where most of this action happens. It's the healthiest soil. It's the most biologically active soil. There could be 100,000 different root exudates from plants, so different biochemicals that are dribbled out through the roots of the plant, and up to 150 biochemicals in food, which are micronutrients. So if the plant makes something to dribble out through its roots, that chemical exists in the plant structure itself. But it's not a one-way street. There are things that are made in soil that are passed back to plants that become part of the nutrients of food. Finally we'll get on to some GrAiNZ, geez. These are just some big numbers for you to think about. Between 1961 and 2013, the area of land planted to wheat, rice and maize increased from 66 to 79%. Doesn't sound like a huge increase. And we grew less barley, millet, oats and rye and sorghum. So essentially, we dropped the nutrient content of our grain load. Just simply on, we're not talking organic, we're not talking healthy soil, we're not talking anything else except growing different species. Not even different varieties, just different species. Sorry, I'll just go back to that. So this is the sort of decline that we're seeing, the nutrient decline. So that's the sort of problem we've got with if we only grow certain grains and not a lot of grains or a variety of grains. We actually affect the amount of nutrients available to humanity. Between 61 and 2011, the protein, iron and zinc contents in the global cereal supply declined by 4%, 19% and 5% respectively. Okay, so that's just looking at the cereal supply as a whole. Again, we're not talking about organics, we're not talking about healthy soil, we're not talking about regenerative agriculture, we're just talking about what was available. So I want you to imagine this. If the roots of wheat in a 1 hectare field, right, organically, pretty healthy, right, the roots can stretch 46,000 kilometres in length. That's a lot of root mass in a 1 hectare field, right? That's a crazy, crazy amount. So it's greater than the circumference of the Earth. So if you linked all the roots together of a 1 acre of wheat, that's how far they can spread. And we're talking healthy wheat, healthy soil. But the fine fungal threads, the hyphae, they can stretch over 2,000 times as far. Now, you've got to remember, if you've got some phosphorus or calcium or magnesium, whatever, boron, selenium, if it's 2 millimetres away from the end of the plant root and you have no soil life, the plant cannot access it. But the fungi can access it. I like this one, 2017 study from India. So we're looking at, I'm interested in soil life and biology. So they got 3 different bacteria from the rhizosphere of plants, then bred them up and poured them on the roots of wheat. They just added 3 species. Now, we're talking in 2 handfuls of soil, 10,000 species. They found 3, right? We're not talking complexity. We're taking a very simplistic view of it. But look, they increased the level of nitrogen, phosphorus, copper, zinc, magnesium, and iron. Adding 3, only 3 out of 10,000 species, they increase the plant height and yield. So what's possible with biology is utterly amazing. The wheat we eat today is 22 to 39% less nutritious than it was 100 years ago. Now, when I'm talking less nutritious, I'm talking about some pretty big things: iron, copper, sulphur, phosphorus, selenium, and zinc. Right? So the way we've bred wheat, that's actually what we've done, is reduce these minerals in wheat. But we're not even looking at micronutrients, phytochemicals, tiny, tiny amounts, those 150,000 biochemicals that could exist in your grain. But this is what we do know over a 100-year period, because a lot of these things you couldn't measure phytochemicals and stuff 100 years ago. Dwarfing wheat, often lower in protein, but more importantly, it has 18% less photosynthesis. Now, I want you to think about this if you're a grower in the room. So dwarfing wheat, the reason we go dwarfing wheat is because if the wheat gets too big and it's got a really big head, the stem can't hold up the heavy head, because we've bred wheat to go from like 3 seeds per head to 30 or whatever it is over the last 500 years. So you have a lot more seeds in the head. So what we did is said, oh, we need to grow really short varieties. Now, that's fine for humanity, okay? But if you cut down photosynthesis by 18%, you have reduced the food supply to soil, the amount that soil gets to eat. You've cut its food supply by 18%. If you then do a summer fallow, which I know is pretty popular in the big grain industry, so summer fallow, for those not in the industry, fallow means resting. Summer fallow, from the grain growers I've talked to, what they do over summer, they don't want to waste any water, so they don't want any plants actually growing in the ground over summer. They spray it with Roundup or some kind of herbicide, so everything dies, so they're not taking water out of the soil for a few months. But what you're actually doing is starving soil to death, because the foods, you cut off the food at its source. If there is no green living plant, you have no food source building. Things in the soil can eat dead stuff, but only some things eat dead stuff, and they can only do it for a certain amount of time. And the more dead stuff they eat, the lower the carbon becomes, the lower the organic matter becomes. So these are just things to consider. Variety counts. So acid-resistant wheat. So we can grow wheat in areas that we didn't. I'm going to talk wheat because wheat's the one that's most commonly researched. There's lots of more money in wheat than there is in sorghum or triticale or anything. Acid-resistant wheat can mask poor soil quality. So we now know you can grow wheat in pretty much anything. You can grow an acid-resistant one. You can throw artificial nitrogen at it, and you can get it to grow. Okay, but can we do that forever? Probably not. Because what happens, things like this, acid-resistant wheat, hinders the growth of the usual rotational crop. So if you want to plant a cover crop like we did, you're actually going to create a problem for the crops that you want to grow maybe in between. So even if you are trying to look after your soil and grow a cover crop in between to fix nitrogen naturally using legumes, you're going to end up with a problem just by variety. So it's something else worth considering. This is my favourite thing ever. Now, we're in a room, I presume some of you are growers, some of you are millers, some of you are bakers, some of you are doing all of it. I got into food, into growing food because I wanted to eat, right? And I wanted to eat more and I wanted to eat well. And I love this study because now I'm interested in soil, and I'm interested in soil because I want to eat more and I want to eat better, right? And this is the classic example. In 2013, they looked at the flavour of bread, and they wanted to look at a really old variety of wheat, and they wanted to look at a modern variety, and they grew the wheats in virtually identical plots. So they grew the modern variety, they grew the ancient variety, and they grew the modern variety, and they added one fungal strain. So remember, there's hundreds of, and thousands of fungi in the world, but they found a particular fungal strain that they thought might be beneficial. And then they gave it to a group of testers. Now, these people were trained testers. They are trained in being able to analyse the texture and smell and flavour of bread, and they baked bread. And a single fungus gives the wheat more and different micronutrients. So, if the fungus gave it more different micronutrients, you'd be able to taste the difference in the bread. Okay, so, because what's happening, the plant is gaining more stuff from soil, essentially. It's getting more minerals, more phytochemicals, all that kind of stuff going on. So if the grain is getting more of that, you should be able to taste the difference in the bread. It's a long way from soil to bread, but they could taste the difference. And they had an electronic nose that can, pick up chemical differences in smell, and the electronic nose could tell the difference. One single change in a fungal strain that was added to the soil changes the end product, the flavour of the bread. And I love this because it shows the connection between the biology beneath our feet and the flavour of the food we eat. So it's our choice. GrAiNZ, really one of the big problems is because oftentimes it's grown in greater scale. Generally, wheat, which is the great example. Generally, when we grow wheat, we lose carbon in soil. It's much harder to increase soil health growing grains en masse unless you have lots of rotational crops, maybe put animals in the system. It's much harder to look after that soil than it is to look after, say, the grasslands that I look after, or a market garden where they have lots of inputs. But what I'm really excited about talking to you about this today, because actually GrAiNZ is the great frontier. Because we know there are people who can do it and are doing it on small and even big scale, but it needs to be spread further, because every time you're looking after soil health, you're looking after the flavour of the bread, but you're also, all those things in bread or whatever you're making, pasta, beer, it doesn't matter. All the things that exist that give it flavour are also things that are doing us good. So that connection between soil health, human health, planetary health, for me is a really clear line. And what connects it all is pleasure, the joy of eating. Because actually, every time we nail that, we get a better tasting product for the person at the end. Thank you.
Thank you, Matthew.
Sorry, just going to grab my water.
We're so grateful to have you here. Are there any quick questions for Matthew?
Thank you, Matthew. That was amazing. Right at the end, you sort of looped it all together between the soil and then the end product. When we're talking about like nutrient density or nutrition or even flavour itself, where are we at with, forgive me, I did study science, but where are we at for sort of measuring that? I mean, we have anecdotal experience for the foods that we eat. And you know a tomato from your backyard tastes different from one from the supermarket. But is there something that, or are there methods that are being looked at to sort of track that or test it?
Yeah, so the single best measure we have currently to measure nutrient density, I'm not talking fat, protein and carbohydrate. I'm not even talking vitamins and minerals. Vitamins and minerals are kind of like 1920s science. I'm talking 2023 science. The best tool we have to measure that is the human palate. Because human nose can smell it to 1 billion different smells, and a smell is an indicator of a chemical that's in food, and the chemicals in food are those things that are made by the plant to talk to soil or made in soil and passed to the plant. And so that's the finest tuning we've got. There are people coming up with things that you should be able to take in the next couple of years into a supermarket and compare the broccoli in a supermarket compared to your organic grower, and be able to compare nutrient density. That's the holy grail, but we're not quite. It's in a testing phase apparently still, and I don't know how expensive it'll be, but that'll make the difference, because you'll be actually, for growers, it'll be saying, oh, you don't just get paid per kilo, you'll get paid for quality. And the quality isn't just how green it is or how long it lasts, it's nutrient density.